Hello everyone, good day. Welcome to another session for this lecture presentation for chemistry for engineers. Especially those second year chemical engineering students from Xavier University who are watching this lecture video. I'm your instructor for today, as if I'm working in Xavier, right? I'm your instructor for today, and yes, I will be discussing one of your pre-final topics, which is the topic in soil chemistry. But before that, I will just going to introduce myself because I know most of you is not familiar with me. So here. By the way, my name is Judy Mardi Larmo. You can call me Ate Judy if you want to reach out. I graduated with the course Chemical Engineering also in Xavier University and just last March 2020. So same with your Kuya Dale. We're batchmates and currently both of us and our other batchmates is working or studying hard for our license. So uh, hopefully next year again. So please pray for all of us. And anyway, I'm working also right now. I'm a chemistry part-time instructor in one of the most well-known university here in the city. So uh, I guess um, I guess that's it. I don't have anything to say about myself anymore. So if you want to uh, if you want to reach out to me, you just have to email me. I will give you my email and then reach me out on Facebook. So my name is stated there. I'm Judy Mar Alamo in Facebook. So without further ado, let's get started in our lesson. So for our discussion outline today, I will be going to discuss seven major topics under this soil chemistry. So the first is the definition of soil. Second is major soil components, and then the different characteristics of soils, the developmental soil horizons, as well as the factors that could affect the soil formation, and then the different soil forming regimes, and then the different classifications of soil. So throughout this discussion, I hope that you will understand more on the topic and as I read your lecture notes, I find it very very interesting to learn, and then it includes a lot of uh, uh, new terms, but hopefully as we go along, we will be able to remember those terms and it's really applicable. It's really applicable um, if you want to go through the next lectures. So I hope you understand the different major terms first before you go through. So, okay. So here we have a definition of soil. So you can see in the picture, it's really familiar for us. We know or we have seen soil, di ba? We have seen soil in our lives. So it's one of the most important natural resource that is essential for sustaining Earth's environment. So um, as the definition here, soil it is the unconsolidated cover on the surface of the earth. It is composed primarily of decomposed rock materials and varying amounts of water, gases, and organic materials, and it covers most land surfaces with a fragile and indispensable mantle. It is also capable of supporting plant growth. So Soil, it has also been called the skin of the earth, and its condition and nature usually reflect on the environment under which it is formed and exists today. So, also, soil responds to different climatic conditions, especially to temperature and moisture, and to the land surface configuration itself, and then to the vegetative cover on the different types of plants and its composition, and to the microorganisms or animal activity. So throughout our discussion, I'll be discussing four types of soil. So dili lang sana ako siya i-define here, but along our discussion, just be familiar that I'll be discussing uh, clay, loam, sand, and silt. So if I ever mention this in our discussion, I hope that um, along the way I could define them, and then by their physical appearance, you would have an idea what clay is, what loam is, and the sand and silt. So I think the most familiar that you know is sand. So yes, let's continue. So here, because soil, it develops in response to its environment and with its different characteristics and its conditions under which it is formed. So soil is an exceptional example of integration, and it overlaps among Earth systems. So what I'm talking here, the different systems, is that the atmosphere, the biosphere, the lithosphere, and then the hydrosphere. So this is an integrated system, but it can be divided into forming products. So as you can see, um, soil is between among them. Uh, Before I will discuss why soil is connected with this four Earth subsystem, to I just want to introduce to you this four. So this lithosphere, actually, this is the part of the planet that is composed of rocks and minerals. So it includes the solid crust, the molten mantle, and the liquid and the solid parts of the Earth's core. So so usually, uh, in many places, the geosphere develops a layer of soil here, in which nutrients become available to living organisms. And then it provides an important ecological habitat, and there are different bases of many forms of life here. Second here is the atmosphere. So the atmosphere, this is the gaseous layer surrounding the Earth, and it held to its surface by gravity. So the atmosphere here also absorbs water, usually from the Earth's surface, and it's using the process of evaporation. And then it acts to redistribute the heat and moisture across the Earth's surface. For the hydrosphere, usually it consists of those parts of the Earth system in its liquid form. So it could be gaseous or solid or ice. The hydrosphere includes the Earth's oceans and seas and ice sheets, the sea ice and glaciers and lakes, rivers, streams. This includes both saltwater and freshwater systems also. And the moisture, especially the moisture found in the soil or soil water and within rocks. For the biosphere, it contains all living organisms, and it is intimately related to the other three spheres here. Most living organisms require require gases from the atmosphere, water from the hydrosphere, and then the nutrients and minerals from the geosphere. So the question now is that what is actually soil made of, and what does this the if you imagine? if you scoop a certain amount of soil using a shovel, what what are these soil composed from? So uh, uh, for the next slide, I will discuss to you the soil function as a open system. So you imagine there are the uh, open system. You know what open system, right? So there are matter and energy that flows in and out of the soil, and some are also held up in storage. So if you understand these flows, the inputs and the outputs, so the components and processes also involved, you could also be familiar with it. So soil actually vary from soil to soil. So you have to appreciate or to understand its complexities and its critical natural resources and its function to the environment. So here we will discuss the four components of soil, namely inorganic material, soil water, soil air, and organic matter. So these are the four major components of the soil. So from a study, so from a certain study, uh, 25% of the components of soil usually is air, and then 25% food is water, and then for mineral material, or these are inorganic material, so 45%, and then 5% lang ang organic matter. So uh, the further slides or the next slides, I will discuss these four. So we'll go start with inorganic materials. So this is also known as mineral materials. This uh, um, includes insoluble minerals found in soils that are combination of the most common elements of Earth's surface, such as silicon, aluminum, oxygen, and iron. So if you say insoluble minerals, these are constituents that occur as solid compounds. And it can't be dissolved in water. And some of these insoluble minerals are usually found in air or water that are essential for the components of soil. So um, we have also soluble minerals found in air and water, which includes carbon, hydrogen, nitrogen, sodium, potassium, zinc, copper, and iodine. So these inorganic material, usually they are the ones that sustain the soil deficiencies for specific plants. Uh, Soil deficiency here is something uh, that certain matter that soil lacks. So introducing them, the process of soil fertilization, this is the process of adding certain nutrients or other constituents to the soil in order to meet the conditions that certain plants require. So the addition of of these certain nutrients are usually inorganic material. So also we have soil water. So soil water is also known as capillary water. So we will be mentioning capillary water often in this presentation. So if I mention that, it usually talks to soil water. So it is not pure, but it is a water solution that contains soluble nutrients. So the function of soil water, it serves as a stored water supply for plants. And it also supplies both as an ingredient and a catalyst for chemical reactions that sustain life, and it provides nutrients in a form that can be extracted by vegetation. And the original source of soil moisture is precipitation. The what what precipitation is actually a process. Here, precipitation happens when rain, suppose there's a rain and then it falls on the land. Most of it is either absorbed on the ground or it runs along the soil or down slope. So water seeping through the soil washes over and through various soil materials, and by doing so, it dissolves some of these materials and carrying them through the soil. So basically, we have also this concept called gravitational water. So this is the one that I'm talking about. It is the amount of water flowing down the downslope as rain happens. So let's look at this figure to see where the water in the soil is found in several different circumstances. So water here, it goes down through the soil. It goes down through the soil, and under the force of gravity, so we have this gravitational water. It moves downward through the voids, through soil particles, toward this water table here. So by doing so, actually this water table here, this is the level below which all available spaces in the rocks and soil are filled with water. So as a consequence, water cannot go deeper. So the quantity of this gravitational water in the soil is related to several conditions. So it includes the amount of precipitation and the time since it fell. So because as the longer time it goes to the soil, some of these will evaporate, and it also take into account how easily the water can move through the soil and the spaces available for water storage. So now let's see here. Now let's see how this gravitational water functions in the soil in several ways through this figure. So first, gravitational water, it moves down to the soil, it takes up with finer particles, or as I said, clay or silt here. So if I say fine particles types of soil, this includes the clay and silt. So usually it comes from the upper layer of the soil. And then this downward removal of soil components from the topsoil is called the process of elevation. So this here, gravitational water is going down, it's moving down through the soil, and it takes up those finer particles, which are usually the clay and the silt, from the upper soil layers. And by doing so, we have the process of elevation. So, and then we have also another process. If gravitational water continues to move downward, it deposits the fine materials that it gets from the upper layer, and uh, uh, usually it deposits in the much more lower level of the soil. So this process of deposition of fine materials by water is called the process of elevation. So here in this picture, we have the process of elevation, below elevation. So this is the deposition of fine materials from the upper part of the topsoil. So also, as gravitational water continues to move downward, so it dissolves soluble inorganic materials or minerals, and it carries them more deeper on the levels of the soil. So perhaps it could be on the zone that where all of these open systems are saturated already with this soluble inorganic materials. So by doing so, we deplete these nutrients into the upper soil by the process of leaching, so the process of leaching using the flow of water. So leaching here is the process of depleting nutrients in the upper soil by the thorough flow of water. So in summary, as precipitation happens, as precipitation happens, gravitational water wash out the fine particles and goes it into the deep part of the soil, which is called elevation of fine particles here, which is the elevation. And then as the gravitational water more goes more deeper, it deposits the fine particles. So this is the process of elevation. And then we also take into account the soluble inorganic minerals that are carried into a much more deeper levels of the soil. So it deposits on on saturated spaces along here. So by the process of thorough flow of water, these nutrients will be distributed, and the process is called leaching. So another component of soil, we have soil air. So soil air, it is 50% of the soil consists. We know that 50% of soil consists of voids between soil particles and between clumps. So the clumps here are the aggregates of soil, and when these voids are not filled with water, they contain air. So it's likely to have less. The air also is likely to have less oxygen, more carbon dioxide, and a fairly high relative humidity. So compared to the composition of the lower atmosphere, the air in the soil usually it takes to have less oxygen and more carbon dioxide and a high relative humidity because the presence of capillary and or the soil water. So for most microorganisms and plants that also lives in the ground, uh, soil air soil air here supplies oxygen and carbon dioxide necessary for them for life purposes. So it's also a very big help for those microorganisms living in the ground. And then and then the problem of water saturated soil, it is not they are not necessarily excess water, but that if all pores of the spaces of the rock is filled with water, so there is no air that can go in. So the lack of air is why many plants and animals find it difficult to survive in water saturated soils. It's very important that those voids of the soil uh, must be contained with air to help those microorganisms also live in the ground. So for the last major component of soils, we have uh, organic matter. So this organic matter contains humus. These are the decayed remains of plants and animal materials, partially transformed by bacterial action. So humus actually it is an important part of, of plant growth or vegetation process because it acts as a catalyst usually in chemical reaction by which plants here extract soil nutrients and minerals that it provides to the soil. So uh, a soil that contains humus is quite workable and has a good capacity to retain water. So it also provides food source for microscopic soil organisms. Example here could be bacteria and fungi, up to the earthworms and many other microorganisms found in soil. Also, organic matter, these are animals contribute to the development and enrichment of soils by creating humus for plant litter and by mixing organic material deeper into the soil. So, in addition, chemical and mechanical functions of plants and their root systems are usually integral part of soil forming systems. So they use mostly organic matter to sustain the nutrients that they need in order for them to grow. So this is the diagram for the four major components of soil. So I've mentioned here that these are the we have here the inorganic inorganic materials. So it's mostly on the outer layer, and then we have found here the soil water. So we have here the water, and then we have the organic matter. So I think this is the humus that is discussed in the past slide, and the voids here, they are composed of air. So this is the uh, diagram or picture for the major components of soil and its designation. Now we go to the different characteristics of soil. So uh, soil soil properties can be readily tested and examined when they are being used to describe different soil types. So the first is that we have color, texture, structure, and acidity or alkalinity. So I'll be discussing these four also. Let's start with color. So most people actually, kita, we are aware that soils vary in color from place to place, right? So uh, usually color, this is the most visible attribute of soil. Very, very physical and very visible. Okay, usually this is the first one that we see. And then it vary in color, usually from black to brown to red, yellow, gray, and near white. So so later I'll be discussing what what composition does soil had if this is this color. I mean this is the color and what does it contains. So also a soil's color offers a clue to its physical and chemical characteristics. So in this picture, this is called the Munsell Color Book. So this is the color book that is usually used by laboratory soil scientists when they want to describe soils in the field or samples that they collected. And then this is a standardized soil color book, and usually it is used to identify what type of soil have they collected. So it's a standard guide usually for matching and recognizing precise color of soil types. And this book also includes common soil colors, but each color can also appear in a wide variety of tones. Here, um, if you collected, for example, if you collected a soil that is color red, usually it indicates that oxidation has been an active process here, and oxygen has chemically reacted with the soil minerals like iron. So if you see a red color soil, usually it contains it contains iron minerals, and oxidation happens. It reacts with oxygen, so that causes its color to be uh, reddish color. So for blue, silver, and gray, usually these tones mean that the soil has likely been reduced. In other words, oxygen has been removed from the soil. So even if um, even if this type of soil also consists iron minerals, then it does not react with the oxygen on air, so it has less oxygen content. That's why the color here, instead of red, it becomes blue, silver, or either gray. We have also white. I did not color it white because you could not see the word. So, but I know what you know the color white. So, usually it denotes that calcium carbonate or salts such as sodium chloride may be present in the soil. So, if you see this type of soil color, then it denotes that salts are present. And then if we have also black, so a very dark color may indicate a high amount of organic material present in the soil. So basically, black color man gid ang ato ang soil na usually here sa atong lugar. And then people, as what I've observed, most of the planters or farmers, they use black, a very dark color soil, kaya they know that it contains most of the minerals and nutrients and organic material that is good for them uh, to help them grow the plants that they want to grow or plant. So now we go to another characteristics of soil. This is called the soil texture. So soil texture, they refers to the size or distribution or sizes of particles that make up a soil. So here, in this picture or diagram, um, we can see that mostly in clay type of soil. So here, the diameter ranges usually from from uh, I mean, for clayey soil, the diameter usually ranges less than 0.002 millimeters. So it's very it's very small. So it's invisible at this scale. So if we enlarge this, this would be the picture. So in salty soils also, the diameter range from 0.02 millimeter to 0.05. For sandy, these are quite big soil particles. So the diameter usually range from 0.05 to 2 millimeters. So particles larger than 2 millimeters, these are usually treated or regarded as pebbles, rocks, gravel, and then other types of high particles already. So here, the texture of the soil also can be represented using this diagram. So we will be doing a little game here. So it's a game, but it's not. You could understand the soil texture using this diagram as well. So the proportion of the particles according to the size determines the soil texture. So for example, here, a soil composed of 50% silt-sized particles. So before we answer that, we take into account that this area here, these are the percentage for uh, silt, and then the red here are the percentage for percent clay. So the percentage here are from zero, increasing from 0 to 100, and then for percent soil is from 0 to 100. So in the bottom part, we have the percent sand. So for example, a soil is composed of 50% silt-sized particles. So we want to find the 50% here in the percent silt side. So this is the 50%. So we're going down. We take this in we take this part here. So we have also 45% clay. So clay here, we want to find 35%. So it's between here. So we take account this area, these two. And then it also contains the 5% sand. So here we want to um, find 5%. So here 5%. Okay, so what you're going to do is that we would be identifying what type of soil is given or described based on the percentage. So we go we go upward. Sorry, I have a very crooked line. We go upward, and then we also take this horizontally. So you could see that the three lines intersect here. So it's a silty type of soil. So we have described here the soil texture based on its composition. So here, another example is that a second soil sample now is given 20% silt, 20% silt. So here, and then 30% clay, 30% clay, sorry, here, 30% clay, and then 50% sand. So we would identify what type of soil here. So we're doing the same thing that we did. So we have identified the point P here. So this is the sandy clay loam type of soil. So now I have a question for you. So you could answer this in your free time. So what would be the soil type if it contains 40% sand, 40% silt, and 20% clay? So again, 40% sand, 40% silt, and 20% clay. So you can tell me what the answer is. So you could answer it now. So okay, I just give maybe 5 seconds. 5, 4, 3, 2, 1. I guess okay na. Okay, so the answer is if we have 40% sand, 40% sand, 40% silt, and 20% clay. So what we get is a loam. So here we'll be defining what loam soil is. So loam soil, this type of soil usually, as you can see, most of those types are in the between this triangular diagram, and those none are those on the other sides. It's the other type of soil already. So this loam soil is very best suited for supporting vegetation growth. So I guess we already understand it. Now we go to another characteristics of soil, which is the acidity or alkalinity. So acidity or alkalinity, it tells if the soil is fertile or infertile. And then it means that there are different chemical processes that takes place in most soils and plant systems that could make this soil fertile for plant growth and infertile for also not applicable for plant growth. Then a lower pH means a greater amount of hydrogen ions present. So lower pH here means a higher acidity. And then a higher pH also means smaller amount of hydrogen ions present or higher alkalinity. And then soil acidity or alkalinity, it helps us determine the available nutrients that affect the plant growth. So the levels of acidity or alkalinity is measured in this figure here. So usually it's from 0 to 14. And this is the usual pH scale when we got from basic to acid. And then this pH reading indicates the reactive hydrogen ion present for the different types of soil. Then this pH also is quite logarithmic, meaning that every changes in a whole number or whole pH number represent a tenfold change also. So it is also an inverted. It is also called an inverted scale. So low pH value indicate an acid soil, and a high pH usually indicates an alkaline or basic soil. So for rainfall days, heavy rainfall. So we have understood that the leaching process will increase. So it usually represents the soil elements such as sodium, potassium, calcium, and others with hydrogen. So the desert soil tend to be more alkaline or more basic, and soils in humid regions tend to be more acidic. Now we go to the development of soil horizons. So, uh, soil development soil development begins when plants and animals colonize rocks or deposits of rock fragments, the parent material on which soil will form, and this is examined by doing soil profiles. So what you can see in this picture is that this is a vertical cross section. Usually, this is a vertical cross section of the soil from the surface down to the parent material. So when we say parent material, these are usually referred to as rocks or usually big rocks or big soils that are being degrade or kanang nabungkag siya in a long time, then it results to kalalong siya along the time. So a soil profile here is used to examine the composition, the color, the structure of this type of parent material or rocks or deposits. They usually dig a pit by vertical walls to clearly show the different variations of those soils already. And then it's an important tool in nutrient management, the soil profile. So by doing this, we can gain a valuable insight about the soil fertility and the different types of, of soil changes happens. So if if it's applicable, soil profile could also identify the amount of soil that weathers, and then the organic matter that decompose. So here I will be discussing soil horizons. So soil horizons, these are the well-developed soils, typically on exhibit zones or distinct layers that are distinguished by their physical or chemical properties by soil profiling. So not just kanang they know the structure, the color, or the texture and the composition of the soil from the parent material. They usually kanang make layers or study the different layers of soil, resulting in their soil profiling. And that layers they have they can distinguish different physical and chemical properties. So soil horizons are usually designated by letters here. They refer to their composition, to their dominant process, to their other position based sa soil profile. So we have here O horizon. So this O horizon usually this is the layer sufficient for vegetation and moderate and have moderate organic decomposition. So Meaning, Ani, is that they have this layer of soil have a high composition of humus here. So it's very rich in organic material. And then for A horizon, this is commonly referred to as topsoil. They are dark in color, and it's because of the concentration of the different decomposed organic matter gapon. So beneath the A horizon, some have a lighter colored soil. We have E horizon, namely after the elongation process, katong balikon nato itong process sa elongation that as the precipitation or the water washed off the nutrients and minerals from the soil, then the nutrients will go, especially the fine particles which are the clay and the slate, as silt to go to the small part of the deeper part of the soil. So here, the E horizon here, they are downward. They are the downward removal. There's downward removal of soil components between the topsoil and the water. And then again, for letter B, this is the B or C horizon here. For B horizon, this is the starting of accumulation of the nutrients. So we have here a line or gypsum. You could find it here, deeper in color zone than maximum accumulation, because the more lime or gypsum deposits here, the more darker, the more reddish it becomes. And then it starts in the transition of C here. Sea horizon, it is a weathered parent material, partly weathered material, parent material from which the soil has developed, and it could be into different fragments of the bedrock directly beneath or below the rock materials that had been transported or deposited. So as I mentioned earlier, the parent material, these are the colonized rock, rock and fragments, different soil fragments that are that are kanang that are decomposed or nabungkag siya along the time. So we have also from the lowest layer the R or the regolith or rock layer. These are the unchanged parent material, meaning it never undergoes any colonization or wala siya nabungkag. So so it's either bedrock or rock fragments transported directly to the site of water by wind, glacial, or other surface processes. So this process is that to identify the different soil horizon. This is used usually by soil scientists to determine the different physical and chemical properties of the soil that they have conducted due to soil profiling. So now we go to the different factors affecting soil formation. So the first factor here that we'll be discussing is the parent material, because this is the raw material of our discussion here. So diri gauna tanan na happen ang soil formation. So we will also discuss organic activity, climate, land surface configuration or relief, and time. So for parent material, we have two types here. So usually soils are produced from rocks, which are the parent material through the process of weathering and natural erosion. So all soils contains weathered fragments or rock material, and it could be classified according to these two. So we have residual parent material. This means that these are weathered rock particles that have accumulated in place through the physical and chemical breakdown of bedrock directly beneath the soil. So when parent materials usually break down at the same place, and then kadaghan na siya dito, so that is called residual parent materials. Example for this are igneous, sedimentary, and metamorphic rocks. And then if we have transported parent materials, this means that these are rock fragments that form from soil that have been carried to the site and deposited by streams, waves, winds, gravity or glaciers. So this is also kanang type of parent material na usually nadala lang siya sa tubig, sa other types of transport process na dito sila nag tapok na dayon. So then we have organic material. So organic material usually it is very it affects the soil formation, the way it it reacts, the way it reacts to the beneath the soil to the plants, and then plants and animals, this affects soil formation because this organic material, like the organisms, they usually give something to the soil and to the plants when they decompose. So for plants, magsugod na din na sila o grow if there's a soil, right? So soil forms, plants begin to grow. And then as plants mature and they die, new ones take place. Certain nutrients absorbed by plants, they are returned in the soil after the plants die and decompose. So after they die, soluble nutrients that are not used by plants can be lost through leaching, which can be used to improvise the soil. So that would be the very big kanang contribution of plants also when they decompose and die, they give nutrients to the soil for another for to sustain another plant growth. And then the nature of plant community, it determines the nutrient cycles that are involved in soil formation. So generally, plants forests, they have this term called uh, forest canopy. Usually, this canopy is a protective canopy to prevent the soil to wash out all the nutrients from a heavy rainfall, and then it keeps rain from beating directly on the soil, thus increasing the proportion of rainwater that enters in the soil rather than running off its surface. So, dili mawala ang mga nutrients sa soil because of heavy rainfall. If it's because of the forest canopy that is provided by the usually the trees. And then the microorganisms here, the the fungi, the bacteria, they are the burrowing insects and the animals, other types of animals, and even human. If we die, uh, the process of decay, the process of decay and decomposition, it's aided when did by bacterial, diba, and fungal activity. So it transformed organic matter into a jelly-like mass called humus. So basically, humus is very important for plant growth good. It's an important soil component for several reasons. For one, uh, humus is a primary food supply for soil microorganisms. Good. And without that, these microorganisms could not live and could not execute their way of providing or sustaining growth. So organic material is a big part of soil formation because by doing so, the plants and the microorganisms, they have different inputs for the inputs for the different plants. And then first input is that through rock weathering, so they have achieved the K zone, the dione, and then the nutrients it goes back to the plants. And then the output, these are the groundwater and the streams that flows in from the soil. These are the also some of these also are going to the plants to sustain life. So that's how organic material could affect soil formation. So also for climate, it's also one of the major factor for soil formation because temperature directly affects the activity of the soil microorganism. So which this in turns affects the rate of the decomposition of the organic matter. So here um, in this diagram, in usually in hot region, so in high places, intense activity of soil microorganisms preclude thick accumulation of organic debris or humus. So mas daghang microorganisms that could use humus in hot equatorial region. So because there is a high temperature, it limits it limits the rate of destruction by aerobic bacteria here. And then in colder region, the combination of retarded microorganism activity and limited plant growth results in thin accumulations of organic matter that may be either partially decomposed or unaffected by decomposition. So here, as the as the temperature is increasing, the accumulates humus. Then after a while, if 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 taas na kaayo, so there's a faster rate of destruction of aerobic bacteria, those bacteria that that use oxygen for living. And then here also for ga-decrease po ang anaerobic bacteria. And then the rate of production of macroflora is a type of bacteria also. It's also increasing in as kanang nalang siya mean temperature, then it also starts to decrease as the mean annual temperature also starts to increase. So the climate is a very big factor for soil formation. It shows the amount of organic matter and humus in soil increases increases toward the middle latitudes and away from the tropic regions. Also, we have land surface configuration, so it's also called relief. So the slope of the land or relief and its aspect, it it refers to the direction or even the direction it faces, all influence the soil development. So here, this is an example of steep slopes. So steep slopes, usually they are better drained than gentler ones. The kanang straight slope lang because steep slopes they are they cause less infiltration of water, which retards in soil forming processes. So there's a rapid runoff of steep slopes that can erode surfaces as fast or faster than soil ever developed in them. So there is no soil that will develop on the parent material in this type of land surface configuration. Mas less ang development sa parent material. For gentler slopes, it has less runoff manioff and more water infiltration. So more water is available for soil forming processes and to support vegetative growth. Erosion also is not that intense in this type of land surface or the gentler slopes. So naay mga possibility that soil can be formed from the parent materials that is associated in this type of uh, soil area. Mas paspas ang surface configuration, mas paspas ang changes sa land surface for gentler slopes kay taas ang iyang possibility to form soil from different parent materials. Also flat lands as well. here we have valley floors and flatlands. So valley floors and flatlands, they are usually poorly drained because gravitational water from the rain cannot flow downwards. So, capillary water or the soil water, they could move harmful concentrations into salt and alkaline substance to the surface. So this condition presents a constant problem for emigration. For flatlands. They usually use drainage ditches here to support or to provide to lower high water tables in such instances. So in this type of land surface configuration, it's very difficult to raise the water, and and this type of this type of soil configuration is very difficult to influence soil development. Land surface configuration indirectly can affect or influence soil development by vegetation. Maka-affect dito sa vegetation because steeper slopes, they prevent the development of mature soil, and that would support abundant vegetation. So here, the last part is the time. So soil have the tendency to develop toward a state of equilibrium with their environment in time. So a soil becomes more mature when it reaches this condition. So we have here young soil that are still in the process of alteration to achieve the equilibrium, meaning the the uh, the process of entering the matter and energy in the different forms of these soils are not that dili pa kayo siya na ka uh, ka-abundant. So here, organic material accumulates as plant and other organisms die. So for young soil, that's the only thing that they could do to achieve uh, the equilibrium or para mahimong silang mature soils. For mature soils, they are well developed or stable horizons that indicates the growth indicates the conditions of proper vegetation and plant growth. So we have seen here that they contain greater amount of organic materials present as compared to young soil. Then for immature soil, these are typically poorly developed horizons, and may possibility po na wala gyud sila development. So the parent rock here is weathered, and the fragments for the parent material have been moved upward that cause mga presence of more bedrocks or rock fragments. So wala gid kayo sila process of organic material and other nutrients or minerals to support plant growth. Another effect is that as time passed by, all soils will mature man, but their influence in the parent material decreases, and they increasingly reflect their climate and vegetative environment. So may possibility gyapon that young soil will mature at the certain period of time. So the time of developing the soil is an important to its composition and physical character. So given enough time and proper environmental conditions, soil will become more maturely developed with deeper profile and stronger horizon development. So now we go to the different uh, soil forming regimes. So we have here the laterization, calcification, and the fossilization. So the characteristics that make major soils type distinctive and other types distinct, or they are different from each other, is through the soil forming regimes. So these soil forming regimes vary mainly because of the differences in climates and vegetation. So climate differences here, they produce three primary soil forming regimes. We have, as I mentioned earlier, laterization, classification, and fossilization. So laterization, as depicted here in the first picture, it occurs in humid tropical and subtropical climates as a result of high temperatures and abundant precipitation. So, mas daghan times magulan in this that could cause laterization in these areas. So, it is a weathering process by which laterite is formed. So, uh, laterite here is called soil or rock type that are rich in iron and aluminum. So, so in this process, soil and rocks are depleted into more soluble substances. So, and then we also have a process of puzzolization. So, puzzolization here, I think I mentioned it earlier, kanina. The soil horizon, they have the same process. So, so this is the soil with more rich of organic material, more darker. Here is the katong produced by the process of elevation. Then here is the process of the after elevation, and then fossilization occurs mainly in high middle latitudes where the climate is moist with short and cool summers of um, long winters and severe kanang cold areas did so. So this is the formation of the soil if kanang mag-undergo sila og soil profile. For cool to hot or subhumid climate, so this is the process of calcification. So we could produce a much more dark color uh, type of soil for A horizon. Then for B horizon, lighter color, as, but not that light as compared to warm and cold or moist climate. Then also sa C here, the parent material or katong weathering of parent material, they are usually unaltered. So dili kayo ma-alter ang mga rock formation below the ground in this type of climate. So these are the three major types of soil forming regimes. So we also have additional salinization and glaciation, but we will be discussing more on this sa other lecture. Now we go to the NCRCS soil classification system. So we go to the process of classification of soil na. So soils, like climates, they can be classified and mapped by their distinctive characteristics. So usually this soil classification system, they are the soil classification process, they are they are results from surveys published in books already, and it could help us describe the kinds of soil in a certain regions, and usually they includes maps that show distribution of soil types. So in the US setting, we'll be discussing the US. So they had this system called NRCS, where NRCS stands for Natural Resource Conservation Services. So it's a branch of Department of Agriculture in the US. So these are the 12 largest classification of soil that they have. We have oxic horizon, rich in oxygen. So we will not be discussing all of this na lang, but we will be mentioning siguro here in the later slides some. And then and then also while examining the soil for classification under this system, particular attention usually is paid to the horizon viewed by its texture to characterize the soil. So some of these horizons are below the surface. So when you say below the surface, it's in the subsurface horizon, and then others are some on the epipedons. So epipedons are here. These are the surface layers that usually exhibit a dark shading associated with organic material or humus. So dito sa mostly sa taas-taas na part sa layers soil. So this classification also are they are classification of soils according to the soil order, and then kanigig silang 12 ang na-recognize. So to provide a greater detail, soil orders or this soil horizon can be divided into suborders and other groups, subgroups or families. So these are the ano na lang, these are the 12 soil classification system provided from the book. Actually, there's 9 lang the I here, but the other 3 is not provided in the book. But you could research more on it. So now let's go to the 12. So NCRS or National Natural Resources Conservation Services Classification System. So we'll give you just a short introduction na lang on the 12 before we end. So we have here the empty soils. These are soils that have undergone little or no soil development, and halak horizons, typically because they have only recently begun to form. So usually these type of soils are very recent, immature soils with no abundance yield of nutrients or organic material presence. So usually they are the parent material characteristics. So here we have next is insectisols. So for insectisols, these are young soils with weak horizon development. The processes of A horizon depletion or the elevation and B horizon deposition or the elevation are just beginning. So usually because of a very cold climate, repeated flood-related deposition at a high rate of soil erosion. So um, these soils have the weakest appearance of horizons among the layers. So they are still soil forming types of soils, and then they are also the most abundant in the earth, usually occupying daw almost 22% of all non-polar continental land area. Then we have histosols. So histosols, these are very low bulk density type of soil developed in a poorly drained areas such as swamps, meadows, or bogs as a product of bleaching. So they are largely composed of slowly decomposing plant material. So in this process here, they nanay mga accumulated tissues of dead plants and animals that could uh, possibly results to kanang nutrients in this type of soil. And then the soil like this have started to have high organic content. For andisols, this is also soils that develop on volcanic parent materials such as volcanic ash and dust-sized particles emitted. So these type of soils are they are not very young. They are usually produced after volcanic eruption, then mga volcanic ash usually spreading, and then these soils are acidic depending on what type of volcano they come from. And then they differ from those in other orders because they typically are dominated by glass and short range order colloidal weathering products. So makita ka diri og mga glass particles present in this type of soil such as the allophane. So that is a characteristics of the undissolved soils. So we have gillisols. Gillisols, these are soils that are experienced frequently from freezing and thawing of the ground above permafrost. So permafrost, these are the temperature of the soil ranging from 0 degrees Celsius below. So uh, uh, the soil is kanang inani siya na express or na introduced in this below temperature for at least 2 years. And then these soils can be found in a very high, very cold climates, very limited geographically kanang setting, and then high latitude polar regions. We also have arid soils. So these are soils of desert regions that develop primarily under conditions where precipitation is less than half the potential evaporation. So dili kayo gaulan in this type of kanang soil. So dili sila gakaulanan. So it usually in the surface horizon, the uppermost layer, very light in color, okay, low humus content, dry soil conditions, mostly a year, dili siya kaulanan. And then naay mga accumulation of silicate clay and soluble salts and sodium ion. So usually these are known as desert soils. For vertisols, these are typically found in regions of strong seasonality of precipitation, such as tropical wet and dry climates. So here, these types of soil have high clay materials, and then these clay materials absorb water and increase in volume when kanang they started to form dry, deep, and then much more darker type of soils. Excuse me. Mollysols, these are most closely associated with grassland regions and are among the best soil for sustained agriculture. So mollysols, they are usually thick, dark surface horizon, fertile type of soil. They are kanang long-term exposed na sila for organic materials derived from plant roots. So they are very or naturally highly productive soils, more than 50% saturated with calcium, magnesium, and nitrate. For alphisols, they usually occur in a wide variety of climate settings. They are characterized by a subsurface clay horizon, a medium to high base supply, and a light-colored ochryptidon or ochryptidon. I don't know how to pronounce it. But this type of soil usually they have strong yellowish or I mean reddish color because they have more presence of iron. And then the red clay here soils, they are usually found in United States mostly. They are not occurring in this kind of area where there is very dry, mga warm places, usually in a cold place gapon. So spodosols are mostly closely associated with the podzolization or forming process. They are readily identified by the strong horizon development. So when we say podzolization process, they have experienced elevation or the nutrient reposition. So this type of soil are kanang daghan gyapon siya og presence of organic material, and they are also uh, subsurface accumulation of humus that is complex with aluminum and iron. So second to the last is your ultisols. So ultisols like spudosols are also low in bases because they develop in moist or wet regions. So they are characterized by subsurface clay horizon and are often yellow or red because of the residual iron and aluminum oxides in the A horizon. So basically, what causes the the soil to be reddish type is because of the iron and aluminum presence in the soil. So it's an example. This is the example of that. The reddish type also soil, which is the ultisols. And then for the oxysols, these are the more developed soils over long periods of time in tropical regions with high temperatures and heavy annual rainfall. They are almost entirely rich of soluble bases and are characterized by a thick development of iron and aluminum oxide. So the key basic profile characteristics of oxysols is that they are uniformly textured. They have high amounts of iron and aluminum, reddish Jacobean color, and then they are highly weathered type of soil. So they are they are contained in all depths, no more than 10% of the minerals found in soil, and they have low cation exchange capacity, which is also very very good types of soil. So I guess that's the end of our discussion. So yes, the topic is very interesting to learn. So I hope that you learn something from the discussion, and thank you for listening in this lecture video. So I hope to see you in the next one. So thank you for listening. Thank you.